Well, good morning, everybody. I appreciate the invite. The last time I was here in Tokyo was, in Kobe was about, I think, 12 years ago. So it was high time to come back. Then I talked about HPC, and so today I'm going to talk a little bit about a slightly different topic, which is quantum computing. So to really put everything in perspective a little bit, so I'm a computational scientist, and my goal is to actually deliver scientific solutions to big fetching questions. And that's kind of in the same vein as was outlined by our keynote speaker earlier. So to me, high performance computing or exascale computing, machine learning or AI, and quantum computing are tools to develop so that we can start to solve scientific problems. And quantum computing has a potential to really help us tackle problems of unprecedented scale. What are those? We heard already about that a little bit. There is a potential for algorithmic speedups over classical computing, although I will argue at the end for a little bit that that might not be the only and important aspect of this. What a lot of the scientists are interested in is quantum simulation or potentially efficient optimization algorithms, because those directly impact some of the science that we would like to do with quantum computers. So everybody has heard probably about the quantum computers. They're all here. Oh, it's noisy, near NISQ quantum computers. We're not there yet. The promise is there. But there is still a lot that has to happen to move quantum computing forward so that it can enable advantage for science in the future. You listen and you see almost every week, and you see new advances coming out of the hardware side. They're figuring out ways to increase qubit count, they increase lifetimes, they increase fidelities, reduce errors, and now in the last couple of weeks, literally we see the first demonstrations of logical qubits, which effectively have a level of error correction built into their chips. But that's not the only challenge that needs to be tackled. It's also that of scientific algorithms and software. We can do a lot when it comes to our computational community in the sense of reducing qubit counts that we need to solve our scientific problems, decrease the number of operations, and incorporate, in a lot of ways, error resiliency in your quantum algorithms. When you look at those are not that different as they are from classical computing. It's the same challenge. How can we reduce the number of CPUs or GPUs we need to use? How can we do it with fewer operations? This is more of the fundamental computer science and applied math that needs to happen to make these kind of quantum computers run, or classical computers run and do the science that we want them to do. So I'll give you a slight sidestep in here and talk a little bit about the quantum information sciences effort that are happening at Berkeley Lab. So we actually are tackling problems across the full stack. From the top, we work on algorithms, software that really help us advance science on quantum computers. We build tools, control protocols to harness quantum computers. We design, actually, and build prototype quantum processors, controls, and sensors. And we're also now, in the last couple of years, started to build a prototype quantum network and quantum computing testbeds. And I wanted to stress that the quantum computing testbeds, the advanced quantum testbed that we have at Berkeley Lab, is actually something that the community can access. There is an opportunity to work with the researchers at that testbed to really understand. For example, I've developed some algorithms. Can we understand the role of noise in my simulations, in my algorithms, to better control and handle what's going on? So there is an opportunity here, and that is not restricted to just US partners. There is international partnerships possible. Okay, so two of the big programs that I'm going to talk about are the Quantum System Accelerator, which is one of the National Quantum Initiative, one of the 5 National Quantum Initiative centers that is funded by the Department of Energy to really move quantum forward. And another one is an AQC, which is a program that I lead that is focused on the software stack for quantum computing. I'll start with the quantum system accelerator because that's one of the high visible programs right now in the Department of Energy. And it's really focused on catalyzing leadership in quantum information sciences through co-design. And you'll see here this a lot, I think, throughout the things that I'm going to talk about. Co-design is critical. It is bringing together the hardware developments, the devices, the algorithms, and the engineering solutions to deliver certified quantum advantage. That's actually a very interesting challenge on its own. How do you know you actually have quantum advantage? And we do this specifically for scientific applications. By the way, our goal is not to deliver a fault-tolerant quantum computer. Our goal is to be above or advancing beyond the near-term quantum computers that are noisy towards fault tolerance. But a lot of our scientific applications don't need a fully fault-tolerant quantum computer. Nature is noisy. We can deal with some noise. And if you look at most of our algorithms, most of the algorithms we allow to converge to a certain number, especially in the science applications. So our target is really to be somewhere where the quantum computers are accurate enough to actually be able to do real science with them. And I can tell you that the team that has been working on this, which involves a large number of institutions, it's 18 institutions across the US, 2 national labs and 1 DoD lab, have been making a lot of strides, and they are starting to push kind of towards that top, the hill of what we have been targeting, closer to more fault-tolerant machines, but not pursuing that directly. So when QSA was developed as a program, they really looked at what the major challenges were. So we chose 4 obstacles. Systems are imperfect, so we need to understand the performance limiting errors and coherence issues and find ways to address it. We need to also work on controls. Controls are fine at the scale that we are, but think of 1 million or even larger numbers of qubits. Controlling them in an accurate, stable way is a hard challenge. Even if you have hardware, what are the meaningful applications that you can run on a quantum computer? And then we need to have a way to benchmark and quantify that these quantum computers are actually going to give us an advantage. So on the right here, you see kind of the directions that we have taken when it comes to advanced quantum prototypes, control, applications, and benchmarking. And QSA as a center is rather unique among the 5 centers in that it actually has not chosen a platform. It does neutral atoms, it does trapped ions, and it does superconducting qubit platforms. And there's a good reason to do that. Some applications might benefit from a certain architecture over others. So again, this is a co-design aspect. You try to solve a science problem with a certain architecture, and you co-design towards an advantage. And some applications will be better at some platforms, better than on some platforms than others. Just to give you a snapshot, this is something we put together during the halfway mark of this 5-year program, showing that we actually have been making some major advances. We not only have a 256 neutral atom quantum simulator, we actually have been able to do real science with that at that scale. So we demonstrated for materials physicists an important aspect of a topological spin qubit. These are analog simulations, and this is something we have to also keep in mind. Digital and analog might both survive. Nature is analog by nature, it's not digital, and you have to keep that in mind. When it comes to trapped ions, we have built the first 200-ion trapped ion trap that actually can store potentially up to 200 ions. It's being installed or built by Sandia, one of the labs that is part of the quantum system accelerator. It's now installed at Duke, where they're going to try and actually keep 100 trapped ions in that system and control them. I mentioned 3 platforms. So we are also working on superconducting qubits, and we have been able to develop qubit technologies that are leading to a 50x reduction in crosstalk, which reduces the noise, which is kind of part of what we need to do. There's a lot of work more foundationally. What are the operations you want to do on these quantum computers? So we've been working on different types of entangling gates, for example, that are suitable. We're also needing to make sure that we can measure and read out the information that's in a quantum computer. So there's a lot of work on trying to figure out, from a fundamental science point of view, how you can better get information and potentially beyond the noise limits. A good example is the third bullet from the bottom. They measured the gravitational shift with atoms with a millimeter atom sample, which means they were very, very accurate in measuring. These are kind of fundamental technologies that are going to be critical for the success of a quantum computer. So to give you a few snippets of some of the advances that have been made. So this is the world of analog neutral atoms, where they did both analog and digital simulations. This was the first demonstration of a reconfigurable neutral atom system. We can move atoms around and force interactions between them. They figured out how to better load these neutral atom systems, because over time you lose atoms. How do you put them back? Harvard's team that is part of the Quantum System Accelerator really delivered the highest fidelity 2-qubit gate so far. They are in the 99.5 range right now. Now that might not be 3, 4, 5, 6 nines, but actually 99.5 is enough to potentially start to think about logical qubits and have enough accuracy to get reliable results out of it. So those are fundamental aspects on the left. In the middle is more the applications. So quantum magnetism, looking at lattice spin models, using cavity QED to really look at the interaction of spin and photons. And then there's a lot of work that has to be done, and I won't talk about that in general, but there's a lot of work that can be done on neutral atoms. We can do them at room temperature. But what is the advantage of maybe doing a little bit of cryo, cooling them a little bit further? How do you do better control of the lasers that are being used, for example? Do more integrated photonics. There's a lot of possibilities to move this field forward. Then there's also, let's switch to the trapped ions. I mentioned we have the first ever trap that can actually store potentially 200 ions. There's a lot of work on thinking about how you can do integrated photonics. How do you do better light collection? How do you read out these systems better? How can you reduce errors? Well, you can do something like sympathetic cooling by adding another type of ion. So there's a lot of work that is being done to integrate kind of more the fundamental research again to enable simulations. And some of those simulations are shown again in the middle. Some some fundamental computer theorists developed an interactive protocol to be able to quantify a quantum advantage. That's nice as a theory, but it's cool to see it actually being done on a trapped ion system. So they used like 14 ions to actually demonstrate that the algorithm works. They actually had to do something special, and this gets back to a co-design. They actually had to develop a mid-circuit measurements through ion shuttling to be able to enable this. And I already mentioned the gates. Again, a lot of what you see here is when it comes to the right side on advancing technologies, there's a lot of optical technologies that are needing to be developed, integrated, smaller, and being able to improve the fidelity further than where they are right now. So on the superconducting qubit, I already mentioned that we have an approach to get much less crosstalk, which is built really on what's called a flip chip type technology. So we're really pushing the edge on those kind of things. It's not just integration that is important, but also the type of qubit. So there is a lot of work going on right now in Floquet, Kerr-Cat, and grid type qubits. Those have a potential to contain the noise or be a lot less noisy and be able to use those kind of technologies then potentially with some error mitigation strategies to get reliable results. So first example of a demonstration that was done is some entanglement methodology for 16 qubits, looking at a material system, being able to get those results really accurate compared to the simulations that you can get out of this. This is another one where a lot of engineering will have to happen to really make this a reality in the future. There's a lot of work that has to be done on thinking about packaging and flexible wiring and how you control them. So one of the things that we've seen in superconducting qubits is an adoption of a platform that was developed at Berkeley Lab called Cubic. There is an analogous one at Fermi Lab, but we are not only doing this in the superconducting qubits. There is an analogous one when it comes to neutral atoms. There is a standardized platform that people are starting to move towards and then jointly develop that moving forward. And then, as I said, it's all not just hardware. It's also the theory and simulation. It's integral. And a good example is the upper left here. This is some theorists really looking at what you could do potentially with an extended Josephson junction, i.e. you put multiple qubits in a cavity and allow a different type of interaction. Normally, if you go and grow these kind of qubits, you would potentially induce noise, increase the noise, but the way this is done, this is not likely to happen. The hard part of these kind of ideas is how do I control it? So now it's another co-design on how you better control these kinds of systems. You need to do a lot of work on benchmarking. So one approach that has been developed is randomized mirror circuits. Effectively, you run your simulation forward and backward, and you know if the results get you back to zero or not. But there's also a lot of work on machine learning and AI to integrate continuous error suppression in a real-time simulation of on a superconducting qubit. So can we measure in real time some fraction of the information to get a sense of what the errors are and then find a way to suppress them in real time? I'll briefly talk a little bit about the other program, because one that comes to computer science and applied math, this program has really been focused on delivering an open source computing, programming, and simulation environment that really supports the DOE sciences. So this is the program 8QC. It has a large number of institutions again. This was actually a large number of labs that got put together that have been focusing on languages, compilers, and compilers has become a very big thrust in general. Programming, compiling, and agnostic frameworks, scalable techniques to verify, again, you heard that before too, verification, and an interesting challenge, debugging. How do you debug a quantum computer if you cannot, on the fly, pull information out? How do you know at the end that your algorithm actually ran the right thing? So there's a lot of different aspects when it comes to the software stack that you have to start thinking about if you want to provide this to an end user that is not an expert in quantum information sciences. So one of the first things we did is actually develop a kind of a more flexible programming framework. This was done by our colleagues at Oak Ridge National Lab, where we have a very high level, try to get to a very high level programming environment where we literally allow a physicist to give the physics equations and then just tell it, this is how the algorithm you should try and solve it with, go run. And that's, in the long run, where we want to be able to go. And we heard that earlier too, where we have more gadgets and easy to access systems. So there's a lot of efforts that are being put in to think about and develop software tools, not in just Python, also C++. You can integrate it with things like LLVM to be able to compile these kinds of things highly efficiently. Compiling, as I mentioned before, is a critical piece in the tool chain. I would say from a compiler world at this point in time, there is a lot of commercial efforts, which is the ticket, and there's some work on the Qiskit, of course, compilers. I would say Biscuit, which is Berkeley's quantum compiler, is probably the fastest, the most efficient, and the compiler that generates the shortest circuit at this point in time. Most of the compilers work very well for 10, 20, 30 qubits. We have been able to demonstrate through some level of approximation that we can compile for potentially thousands of qubits without a lot of problems. So there is a lot of innovative stuff that happens in here too, because not always do you need to compile to the exact answer. I mentioned already earlier that we may not need a fully fault tolerant. We can handle some noise. Well, you can actually integrate that in your compilation too. And so we have been able to develop some interesting strategies where we do approximate compilation, but just sample and be able to still get the right answer for the but we have been able to verify the right reason. So again, compilation is an NP hard problem. So even for a large number of qubit counts, even for the compilers we're developing, it still needs a level of HPC. So I'm going to switch a little bit more towards my love when I want to do quantum computing, which is how can I do chemistry materials on quantum computers. So this is some work that we did a while ago where we looked at lithium-2 as a potential component of battery materials. How can we get those simulations done accurately, which is not trivial. But we did a lot of special things again. We used some of the fundamental theories. We actually developed a new approach called VQSE, and the quantum subspace expansion was also really moved forward by us early on to develop technologies that allow us to get reliable results out of a quantum computer. This is a co-design effort, not just with the scientists that are chemists, but this is a co-design with applied mathematicians. A lot of what we had to do is solve effectively a general eigensolver problem. Well, you should say that's fine, but noise makes these eigensolver problems very hard. You get some numbers on your off-diagonals on the overlap matrix S that creates an environment that is not readily solvable anymore. So this was really an effort with applied mathematicians to really solve these equations in the most relevant way. And we were able to get reasonably accurate, and this is 3 years ago, at that point in time, on an IBM machine, reasonably accurate results out of a quantum computer. Since then, we have been building some other ideas, and this is a novel idea that one of my postdocs, Katie Klimko, now a staff member at NERSC, really worked on, where we used a quantum subspace expansion, but we did a real-time evolution to get the eigenvalues. We still solve, as it's in the middle, a generalized eigenvalue problem, but we need to measure some information. We just don't do it in the normal basis that we do it in a real-time form. What's interesting about this approach is that we only had to measure a linear number of measurements instead of quadratic. I don't need to measure a whole matrix. So we actually moved to a unitary form, which has a tuplet structure, which is, there's relationships between different elements of the matrix, and it allowed us to do a lot less measurement. Again, we want to be efficient. We want to do less so that we don't have to handle as much noise. Interestingly, it allows us to also extract the maximum number of excited states out of this, and it has worked really well. So there's a lot of work that has gone into, again, the mathematical framework of thinking how you need to space the steps that you are take the real-time evolution in. One of the things that has become more and more important in the more recent times is thinking about open quantum systems. So if you look at nature in general, and this is not just chemistry and materials, this is high-energy physics, nuclear physics, any field, we don't deal with closed systems. A system doesn't live in isolation. By the way, on classical computers, we tend to do systems in isolation, which is not a representation of nature. We add something to it, but to count for that, but still. So we started to develop more smarter algorithms to actually run these kinds of open quantum systems, which allow us to dissipate energy out of the system that we're studying, with some specific algorithms. So this was the first start that we did in 2022. What's interesting is that when we started to throw that paper on arXiv, we got approached by people from high-energy physics, nuclear physics, and they're like, well, this is what we do. We do open quantum systems for heavy ion collisions. So we actually used the same approach for a heavy quark-antiquark pair in a quark-gluon plasma, and we're able to get reasonably accurate results at that point in time out of these kinds of simulations. And I think this is another example of co-design, and not the traditional one. It's different domains of science realizing that there's a lot of analogy in what they're doing. Since then, we've been playing a little bit with adaptive variational quantum dynamics simulations. So open quantum systems is one. Dynamics is another. That is very relevant to most of the science problems we do. So this is not an approach we developed. This is something that was developed out of Ames. An adaptive approach to do this based on the McLaughlin distance. So we took this approach and actually demonstrated that we can do this for something like a Green's function, which is a property that we can measure that gives us an insight in certain physical properties of, for example, a Hubbard model, a materials model. Again, it's a co-design effort. There's a lot of effort that we had to put in here with applied mathematicians, thinking about how you can get better approximates, how you can get your waveforms better using, for example, a Padilla approximation. Okay, so that's close. But how do you do actually adaptive variational simulation for open quantum systems? Well, that turned out to not be such a trivial thing. So we actually did some effort, both factorized, stochastic, unraveled Lindblads. The challenge with this is if we use the adaptive approach and we use a McLaughlin distance to see how far we are from the right solution, that lower bound is not well defined for open quantum systems. If you think about it, there's information moving between the system that you're looking at and its environment, and that does not happen in a trivial way in a real simulation. So we demonstrated this on 4 and 5 qubits, so it's not a large kind of simulation. We had to do a lot of shots, but we were able to get very accurate results for some of these systems and actually being able to do adaptive variational approaches and minimize the computational resources to simulate open quantum systems. Key to this one actually was something that we call the resolution enhancement technique, which really focuses on peaks that are clearly noise and how to eliminate those to actually get really accurate results compared to experiment. I'll mention briefly that error detection, effectively error correction, works and mitigation works. So this is some work that we did a while ago where we actually did a 422, which is the simplest error correction code. We didn't do correction, we just did detection. We can measure how bad the results are and throw those away. And actually we are able to do the smallest molecule in 6 qubit in a minimal basis. Since then, we have moved a lot further. So this is, I would say, has been one of the largest simulations we've been able to do on magnetic materials on quantum computers. This was not a large number of qubits. It's only a 6 qubit system. But the ideas in there on how you do error mitigation allowed us to go to over 200 C0s on top of all the single qubit systems and get a very reliable result out of this. If you look at the blue dotted line that's running around there, that's what you get out of a quantum computer. But there is a lot of information in it, and again, this brings applied math and computer science together to really think about how to do this better. So we did a lot of different levels of error mitigation to able to get to this. What's interesting again, and this is an integration and co-design idea, those advances that we made, the ideas were adopted by a group at the University of Washington that now was able, in the last couple of months actually, run 100 plus qubit simulations with over 300 gates. So they adopted the philosophy and the tools and be able to do actually this at scale, which inherently means that the techniques that we developed actually work really well. Okay, and I'll skip through this. I wanted to just mention that we have been looking a little bit at cloud-based quantum computers too as a black box technique. Again, end users don't want to deal with a lot of the problems. They want to say, here's my molecule, here, go run, and everything should be hidden. So we actually demonstrated this for a real platform with IBM. So we worked very closely to actually do this implementation and run it in an integrated fashion, quantum coupled with HPC. So part of the algorithm that you have to run in what's called multi-configuration SCF can be run on a quantum computer. Part of it can be run on a classical computer. Actually, the most expensive piece you run on the quantum computer. This goal was not to really run a big science problem, but to understand what it means to actually run the algorithms in a hybrid fashion in a way that we could integrate it with an HPC code that runs, for example, on one of the exascale machines. Okay, so I'll skip through this and say that we do a lot. And I wanted to throw a thought-provoking thought out there, is that exponential speedup is not going to be the only important part for quantum. Cost, power, there's a lot of reasons to start thinking about using quantum computers in a different context than just getting exponential speed up. And actually, if you go on this, if you think about the race to the moon, it delivered a lot of ancillary technologies. We see it already in quantum computing too. Quantum-inspired algorithms show up when we show that a quantum computer has an advantage. The Google, IBM are two papers that show, oh, we have an advantage, only to be pushed back by the classical community saying, hey, we have a better algorithm to do this. There's a lot of technologies that are being developed that have potentially implications in other technologies, in, for example, classical computing in the future. So that, I'll leave it with that. And if you want to learn more about what we do, you can find that on these references. Thank you.